So, أول شيء, welcome to every one of you. Okay, thank you for joining us for this workshop, the first workshop of quantum information in Lebanon. So we are going to start, first of all, by thanking everyone who helped this workshop take place. Of course, I'm going to start with the president of the university, Professor Fouad Ayoub, also the dean of the university, Professor Bassam Badran, of course, our director, Professor Youssef Zaatar, the head of the department, Professor Doumit, and of course, all the colleagues, so that I do not forget any name. So it was a really nice experience starting from the Lebanese University where we had no course of quantum information, no research in quantum information, and as they say, we started from the bottom and now we're here. Okay? So we truly hope that we can also continue expanding in that field. The first workshop where we have the pleasure to have Professor Damien and Fred and also Rawad and Raja, who are PhD students at Leipzig. So it's really a pleasure to have that sort of international configuration for the workshop. So as for my talk, it won't be purely a research talk. Of course, there will be a lot of things I will talk about the research that I started 5 years ago and where we are now. But it will also be a bit of the evolution of quantum information in Lebanon, what we started and what are our perspectives. So that's why I have named my talk Advancements of Quantum Information in Lebanon. So I'm going to talk a bit about the curriculum, what I have done, since many of you are also taking the course of quantum information. So in case you are interested in knowing what to do, what studies you have to do in order to pursue a career in quantum information research, what are the different topics that you can do, what I did as a PhD student, and what I'm doing now as a researcher. So that will be the curriculum part. Then I will talk about the first step, which is the very first thing we started in research here at university for quantum information. I will talk about the teaching modules that we have implemented for quantum information. Also the research that we are currently doing. So we are going to talk about the different partnerships we have, the students that are working with us, and finally, the different workshops and conferences that we have attended as a research group here since we started 5 years ago. So regarding the curriculum, I started a Bachelor of Physics at USG in Lebanon. Then I pursued a Master of Physics in Optics, Laser, and Complex Materials at Université de Bretagne Occidentale in France, followed by a PhD of Physics in Quantum Information at Telecom Paris Tech, where I was supervised by Dr. Eleni Diamanti and Dr. Isabelle Zaki. And of course, that's where I had the pleasure of meeting Damien and Fred, who were working also with the same team with us. So my thesis was entitled Multi-User Distribution of Entangled Photon Pairs at Telecommunication Wavelength. So I'm going to be talking about this in a few moments because that's where I started my first step in research. So I'm going to get back to that. Then I've had the chance and the pleasure to be part of this university in 2014 as an assistant professor. So I started here in October, and I also want to take a time to thank all the colleagues who have really been a strong support since I started and have really been to my side. So if it was not for them, I would not be here today. So thanks a lot to each and every one of you. And in 2016, I've also got promoted to Associate Professor of Physics. So, until, of course, today. So that's basically the whole curriculum of my career so far. Now, regarding the first research step and why I said I'm going to get back to the thesis subject that I did. So I started with an M1 research project on how to do a modelization of an entangled photon source to predict the maximum performances that we can obtain. So while I was doing my PhD, the entangled photon source we wanted to create was not only dedicated to do what we qualify as quantum key distribution for 2 users, but for a whole network of users. So the goal of this study was to prove that we could use classical and conventional communication devices in order to distribute entanglement. Now, as most of you know, entanglement is something only particular to quantum physics. It's not something that we can see in classical physics. And we wanted to see if using any classical components would deteriorate entanglement and also quantify that deterioration, to how much it can be deteriorated. So the good thing is that using classical components, we have been able to show that entanglement can be preserved at high quality, and we can distribute entangled pairs of photons at using telecommunication wavelengths, which are basically the goal, because we wanted to use fiber optics, and we have also been able to prove that we still have entanglement. And in order to prove in a bipartite entanglement that it still holds true, we have to violate what we call the Bell inequalities. So the Bell inequalities are the mathematical tool that we can prove experimentally, once we violate them, that there is a presence of entanglement in our setup. And entanglement in quantum communication really helps us strengthen everything related to security. So you really have the possibility to check whether someone is eavesdropping on you, and to also quantify this degree of eavesdropping. So that's the interest in using entanglement for quantum communication. Of course, there are also other applications used in quantum memory, quantum repeaters, as well as teleportation of entanglement. Now, of course, I took the experimental setup I was using in my thesis and tried to model it. So the idea was to create a MATLAB program, a simple MATLAB program. So keep in mind that the M1 student I was working with, which I, by the way, salute, is Rodolphe. He's not with us, he's in Montpellier now. So Rodolphe started really from scratch. He didn't have any course of quantum information. He didn't know what a qubit was, because there was no course of quantum information. And of course, you guys know that quantum physics is already a tough subject. So I had to teach him everything like in just a few months. And in just a few months, he was not only able to understand what was happening, but he wrote a full program in order to modelize an entangled photon source. So I'm really proud of him for what he did. And so the goal was to say the following: how can I define the parameters that I have in that entangled photon source, and how can I see how they are affecting the three parameters that interest me, which are the Bell parameter, the visibility, and the brightness, which are how many pairs of photon I can get per second, or if you want, the bandwidth of that source, allowing me to know how much time do I need if I want to exchange a certain key with a certain quality threshold that I should not get below. So the elements of the experimental setup were defined in the program. Now I'm going to get back to them. I'm just going to explain here in a little scheme what the program did. We had, first of all, to create our photon pairs. So usually when you want to create pairs of photons, you use nonlinear optics. Okay? Nonlinear optics allows you to create from one single photon using the spontaneous parametric non-conversion. It's a nonlinear optic phenomena that can only be explained with quantum physics. You can create pair of photons, okay, using one single photon. Of course, there should be energy conservation. So let's suppose you have energy E for one photon. You can create a pair where the sum of that pair is equal to E. So you'll have E1 plus E2 equal to the initial energy. And from that way, we can, by using those pair of photons, create either directly entangled pair of photons, or we can use an interferometer to create two pairs, or have a probability, should I say, of creating two pairs, and then entangle the whole system together. So we're working with what we call entanglement in polarization. So for people who are not very familiar with entanglement, I'm going to explain it very simply for polarization. Let's suppose you have an entanglement of polarization in such a way that you have two states, HH and VV, together. What that means is that now those two photons, which we call also two qubits, will form one single system. And measuring the whole system will either collapse to having a ket HH, so having a state HH, or having a state VV. And this means that once I measure only one of the two photons, I can guess in what state the other will have projected. So that's the idea of entanglement. So keep in mind that there's no communication whatsoever that takes place once I do the measurement between the first photon and the second. It's really a system that collapses at the same time. So the idea was first to model how do we create entanglement, because spontaneous parametric non-conversion is a probabilistic phenomena. So it has a 10 power minus 9 in, for example, the PPLN crystal to occur. So we need to send a strong classical signal. What I mean by classical is a signal that has several milliwatt of power. So I send a signal that has several milliwatt of power in order to create a few photon pairs. Because in quantum communication, I'm really going to be working with a few photons. I'm not going to be working with big signals. The photodetectors that I'm working with can detect one photon at a time. So it really, the use of small signals is really what I need. So first thing first, we model the emission of the photon pairs. Then, once the photon pairs are emitted, as I told you, there are two ways. Either they are polarized right away after the crystal, or in our case, they need an interferometer in order to create a recombination between the two arms and create the entanglement between the photons. So the entanglement stage has to be modelized with mirror and lenses, where we can assimilate how many losses I have, because no optical component is perfect, so we need to think about how much loss can occur once I'm letting these photon pairs pass through mirror and lenses, etc. Then I have fiber coupling, because I'm working first in free space, and I have to couple everything into optical fibers before going through my telecommunication components. So what happens in the optical fibers is pretty interesting, because you have, first of all, the losses, because coupling from free space to fiber, you have like at most a coupling of 48%, so you lose almost half of your signal. That's already something huge. Then within the fiber you have losses. That's also something you have to consider. And you also have polarization flipping that can occur at any time due to temperature, due to the mechanism of the fiber. So usually you need to tape them on your optical board in order to avoid this as much as possible. But still, you'll still have that problem nevertheless. And once we let our signal, our photons pass through the optical components, we're also going to have losses that we need to account for. And finally, we have the detection stage, which was one of the most crucial parts to write in our program, because what happens is the following. The detectors are not open the whole time. They open according to a signal to trigger them. So they open only in small windows. And worst of all is that once one of the detectors detects the photons, it needs a dead time. So it needs a certain time where it's going to stay latent without any detection before it opens up. So we had to do this modelization not just for one detector, but for 4 detectors at the same time, and see what happens between them. So that was a part that one of the students here, Elie Monzer, who's now in M2 in France, has worked on. So I had the chance to work with these 2 very bright students who helped me really set this program, because it really needed some very tricky programming in order to do all this modelization. And finally, the outputs that I needed were the visibility, the brightness, and the Bell parameter. So the visibility is basically the interference that occurs between the photons of the pair. So we need to model it as a certain sine function, okay? And if the sine function has a visibility of 100%, it means I have a perfect visibility, a maximum visibility, which is what I want. And if it gets really below a certain threshold, it means I'm still classical, I do not have any quantum effect. So I'm accounting the quantum effect by using visibility and the Bell parameter. And as I said, the brightness is the number of pairs per second that I am emitting. So this program, as I said, elements of the experimental setup were defined: SPDC, efficient total loss, polarization flipping, detection characteristics. And once we got our first set of numerics, we compared them with my experimental setup, for which we knew exactly what was happening. And actually, to our surprise, so the experimental setups are reported in this article, Trapato et al., where I'm second author, in the Journal of Applied Physics, which appeared in 2015. And to our surprise, this is the comparison between what we got as numerics and what we had as experimental results. So experimentally, we had a visibility of 85.14. We got with the numerics 88%, so an error of 3.4%, which is quite acceptable for a first try. Then, to our surprise, the Bell parameter had only an error of 0.41%. Now, keep in mind that the Bell parameter is something statistical, so you need to do several runs. And despite those several runs, we still converge to a value that is extremely close. And finally, for the pairs per second, experimentally, we reported 550 pairs, while for the numerics, we obtained 547. So having 3 parameters that agree is actually something pretty interesting. And this allowed us to present these results at the 3e Journée Franco-Libanaise that took place in Lebanon in Hadas in 2015. And so that was really our first step to say, okay, we are starting to do some research. What can we do to go forward from there? So the perspective of this work, of course, there are many things to be done because it's not something that we can really rely on. In order to go towards a publication, we want to make, first of all, the program a bit more broad. So we need to include tomography and fidelity, which is actually the calculation of the density matrix to calculate the purity of the state that we have. Then we want to generalize the SPDC process. As I said, in our case, we talked about the first type where we need an interferometer to generate entanglement, but we also want to take into consideration the one where we emit polarization entanglement right away. And we also want to consider 4-wave mixing, which is another nonlinear effect that occurs in fibers, and that allows us to create photon pairs within fibers. Now, when we talk about telecommunication to people who work in classical telecommunication, let's suppose you take the Alpha company or MTC, or you take Ogero or IDM, anyone, and you tell them, well, let's do a quantum network. Of course, they prefer everything to be fibered, okay? Or to have at least waveguides, not something in free space. So it would be interesting to add also to our calculation the 4-wave mixing phenomena, which allows us to create the pair of photons right within the fiber. Then, in our case, we were using what we call deterministic splitting. It means that once we reach the detectors, we have one detector for the horizontal polarization, one for the vertical. We want to do the statistical splitting case where it does not look at the polarization and distribute them at the detectors randomly. So that's also a very interesting case to add. And finally, what we really want to do is design an object-oriented program under Python where the user will just have to create his scheme by just dragging and dropping the elements and then click run and get all the results that they want. So there's a lot of work yet to be done. And of course, finally, in order to be able to have something reliable, we need to compare it with the whole set of experimental data, not just one article. We need like a whole bunch of articles and compare our results. Now, if they agree, that's going to be awesome. That could certainly lead us to publish something. And if it doesn't, we will have to see what's wrong and continue working on our program. So once this research was done, teaching actually started, and I want to thank Professor Ziad Harbo, who's the head of the master's degree, and he's the one who first allowed us to include a course of quantum information in his master's degree. And it was actually the first year where Rawad, who's now finishing his PhD, started this course. And to my actually pleasant surprise, a lot of students were interested in the field of quantum information, and Rawad came to me and told me he's interested in pursuing an internship in that field. That was the first step, so I'm going to talk about it in a few moments. So regarding the structure of the course, so we start with a course of 24 hours where we talk about 3 different parts. Quantum information, where we define, first of all, what a qubit is, the Bloch sphere, entangled state and product state, matrix fidelity, the no-cloning theorem, and quantum gates. And part 2, where we start talking about quantum computation, the DiVincenzo criteria and universality, which is something a lot of researchers have to look through when we're working with quantum computing. Circuit identities, the first algorithms such as the Dutch JOSA, the Grover, Bernstein, Vazirani, etc. And also, of course, something at the heart of quantum computing and that made quantum computing actually believable, which is quantum error correction. We also talk about decoherence, which is the biggest enemy of quantum information, which is that the system gets sometimes measured randomly, okay, against our will. And how can we fight that? How can we reduce that as much as possible? And finally, in part 3, we talk about quantum communication. So where we talk about momentum and polarization entanglement, different applications of of quantum communication, such as quantum dense coding, quantum teleportation, entanglement swapping. The CH-SH inequality, which is a particular case of the Bell inequality and the one we use to verify in a bipartite system if we have entanglement or not. The Aspect experiments, which was actually the first experiment to show entanglement in an experimental setup. Quantum cryptography, and for 24 hours, that's quite a dense course, but thankfully I've been able to finish the course every year, so despite the students feeling that I'm really going through a race, but I mean that's at least they finish the course and they have knowledge about all of this. So something that also was very interesting and that started in 2018 is that now we have a course in third year for quantum information of 60 hours. So this course allows us to go much more in depth, and we can start, for example, with, of course, an introduction to quantum mechanics here. There's a course, of course, of quantum mechanics, but I mean, we can go through the math of quantum mechanics even more in depth in order to switch to quantum information. So in that course, I rely a lot on the mathematical aspects and foundation of quantum mechanics because I believe they are at the heart of understanding all the different fields in quantum information. So, for example, we start with the Hilbert space, unitary and stochastic dynamics, Bloch sphere, quantum gates, entanglement, etc. Then, of course, I go through a whole course of probability as well because we need them for Shannon's entropy in classical information theory, because we use a lot of classical information theory in quantum information. So that's why I go through that. Of course, I talk also about the no-cloning theorem. Then I go through the quantum algorithms and I talk about Shor factorization, quantum error correction, and measurement-based quantum computation, which is something also we use a lot in our research for the moment. So it's something that really needs a bit of its time of its own. So that's why I'm able to do it in that course of 60 hours. Then quantum communication, where I talk about dense coding, teleportation, quantum cryptography. So it's a bit similar to the M2 course, but I have much more time. I can go in depth. I can do TD with the students, so that allows them to really understand the foundations of quantum information. And finally, something that we hope will occur starting from next year is a modification in the M2 course of quantum information, in the M2 of nanoscience and functional materials. So, because of course, since there are students who started taking the third year course, we do not want to go to the fifth year and do the whole course all over again. But also, since the third course is elective, we do not want people who start from the M2 to have any lack because they have not assisted to the course of quantum information. So I'm taking here a bit of a different approach where I have decided to focus more on information and computing. So I'm going to go here, for example, with more advanced circuits where I introduce the Fourier series and quantum Fourier transform. Also, I'm going to talk about quantum hardware such as the ion trap and the cavity quantum electrodynamics and circuit quantum electrodynamics. So it's something that I have not started yet. It's not something that we see neither in third year or at the actual course in the fifth year, but that we hope we are going to start next year. And we're also going to talk about stabilizers and fault-tolerant computing and the threshold theorem. So I'm really going to go in depth a lot more in the quantum computing because that's the field of research that I'm working on at the moment. So for the research, where we started from that first step. So I wanted that year where we started the course to continue with that project, but we had other plans. The other plans were that we thought, why not work with something more related to quantum computing and a bit more directed towards a theoretical approach. So that's where we got in touch with Damien, and we started an M2 internship with Rawad that happily led to a thesis, a joint thesis between us and Lipsis. So the thesis we are working on, that Rawad is working on, is quantum randomness for quantum information processing. So keep in mind that I really want to say kudos to Rawad because the subject is really not just complicated, but needed a lot of baggage outside of the course that he has taken. Like the course is just the first step to like a ladder that goes way up in the sky. And so there's a lot of group theory that needed to be worked on. There's a lot of aspects in quantum computing that we couldn't see in class together. There's also the theory of graph states that we had to work on. Measurement-based quantum computing, which we didn't see in the M2 together. So I mean, he really did a great job, and I'm not gonna replace him in the talk because you're gonna have the chance to assist at his talk this afternoon. So this started as an M2 internship, and in March 2016, and for now Rawad is in third year and should do his PhD defense next year. Then we also had the chance to work with Marie-José, who was a student in M2 here in our university, and we worked with Damien on a co-direction subject internship, which is quantumness of typical states. So just to give you an idea, the thing that we have is that when we're working with bipartite, we know that a maximal violation of a maximal entanglement equals to a maximal violation of Bell inequalities equals to a maximal quantum effect. Now, in order to put a bit of perspective, quantum computers rely on properties of quantum physics in order to speed up computation for certain applications. Of course, you read a lot now on the internet about different articles about quantum computers and all the hype about quantum computers. And when will quantum computers come out? Are they still something from the future? Where are we now? Who are the companies who are working on quantum computing? Actually, the companies that are working on quantum computing are many, including IBM, Intel, Microsoft, Google, etc. Now, do we have a quantum computer? No, but also yes. What do I mean by that? I mean by quantum computer, we need a quantum computer with a big number of qubits in order to really show what we define as quantum supremacy or a quantum advantage compared to a classical computer. The use of a quantum computer is not to replace your laptops or your smartphones. It's mostly in order to do certain applications that we cannot do at the moment using classical computers, or that might need a lot of time, a lot of computing time. For example, if we want to do the whole model of any atom that is not a hydrogen or hydrogenoid, we would take a lot of time, and we do not know if the computation can be feasible or if the equations can be solved. But using a quantum computers, these things can happen. But of course, a quantum computer which is quite performant, meaning it has a certain big number of qubits, like several thousands of qubits, in order for it to be feasible. We're not, unfortunately, at this stage at the moment to do such computation, but we can do like a few hundreds of qubits. So we can still see some quantum effects, but not a big quantum advantage as the one that we would like to have. So let me just also redefine what quantumness of typical states meant. It meant that when we work with 3 qubits and more, we see that actually having a maximal entanglement does not equal having a maximal quantum effect, and does not equal to having a maximal quantum speedup. So which is completely different from working with bipartite. And we wanted to see what states can allow us to have this maximal quantum advantage. And that's actually where we define what we call contextuality and quantum advantage in magic states, and which is the work of Elie Merhej this year. And the work of Elie Merhej, where he will have a talk on Tuesday afternoon, he will explain to you everything he's working on, and he's also supervised with by Rawad Messir. So that's basically the whole researcher thing that we have started from now, 5 years ago until now. So with Rawad, we have been able so far to publish one article in Physical Review A, called Efficient Quantum Pseudorandomness with Simple Graph States, so you can check it out whenever you want. And we also have several articles which are on the way. And that concludes it for the research aspects. Now for the workshop and conferences that we have assisted to since we started, there have been several. The troisième journée franco-libanaise where I presented the results I mentioned earlier. Then there was last where Rawad made his very first talk, so it was also a big success. Then we had TQC in Paris in France. theory of quantum computation, communication, cryptography. Then QIP in Netherlands. And something very big was Q-Turn, because we obtained a talk at a very big international conference in Brazil that Rawad gave. So also I want to congratulate them on that. Of course, congratulate the whole team in France, because that's not just a solo effort. The team in France also helped us a lot make this thing possible. And finally, something that I'm really proud of is having our first workshop here in Lebanon. So QICA, Quantum Information and Computing Advancements. So sorry for the mistake here. So we really hope that this workshop in the future can turn into a big conference. And also you as students, I'm really counting on you, because let me tell you that I'm really proud of you for everything you're doing. I'm really happy to see that now people are interested in quantum information. You guys send me videos about quantum computing the whole time, and I enjoy watching. I'm saying that 5 years ago, no one had any idea what a qubit was. No one had even an idea what I did as a PhD subject when I presented my work. So now I can see that not only you guys are understanding, but I'm pretty confident that students at Lebanese University will help this field continue to go forward. So congratulations to all of you, and thank you. So if any of you has any questions so far, please feel free to ask. Do not be shy. Yes. Yes. Okay. The benefit of using four-wave mixing, is there another microphone? Yes. Hi. Please, everyone who wants to ask a question, please come down so that you can use the microphone, please. Hey, no, you can use this. Okay. Turn it on.
I just wanted to ask about the four-wave mixing process.
Yes.
What are the benefits of it, and what is it exactly?
Okay, so that's a very good question. Actually, for four-wave mixing, the benefits is being able to have an entangled photon source that is completely fibered. So you do not have that passage between free space and optical fibers, where you use a lot of your signal. As I said, when you want to couple from a free space to a fiber system, you lose like at least half of your signal. So that's very drastic. When you'll have that advantage once you work with four-wave mixing, where you don't have that problem. Now, working with four-wave mixing, how does that happen? You actually have, you need to have a very strong laser, okay, that you're going to send through an optical fiber. When you send this laser through an optical fiber, by sending 2 photons of that laser, they can create another pair. Which are the pair that we call the signal and idler, which are the 2 photons that you are going to use. Now, once everything is in the fiber, what you can do is that you can use diffraction grating to separate your signal and have your first photon and second photon, each one of them separated, in order to rework on your entanglement altogether. So that's the idea about using four-wave mixing. And now keep in mind that one problem we have when we work with four-wave mixing, we cannot work with conventional optical fibers, which are made of silica. Because the problem is that this signal and idler photons that are very weak are covered by a whole Raman diffusion. So the problem is that we need to work with hollow core fibers. So it's optical fibers that are emptied of their silica, and you can fill them either with gas or liquid to shift the Raman problem, and then you're going to retrieve your signal and idler photons. So also just one thing, at the moment we're really positive that we might be able to do something regarding that model, which is pretty accurate, because four-wave mixing is a bit more difficult to modelize than the spontaneous parametric conversion. So we really hope that we have something here that we can work on.
Can you define for me the visibility?
The visibility, yes. So the visibility is actually an interference pattern that you're going to have between the photons of the same pair. So what we do usually is that we have our first photon that goes through a detector, and before that goes through a polarization rotator, and the second that goes also through a polarization rotator and a detector. What we do is that we start on one of the polarization rotators to switch the angle in order to start drawing an interference pattern. So once the two angles are the same, we should be at the maximum of the interference pattern. And once they are crossed, we should have a completely zero, an absence of, so like a destructive interference. So we start to take several points once we rotate the angles, and we draw that pattern. When we calculate the visibility, we take the maximal minus the minimal over the sum of them. If we obtain 100%, it means we are at a minimal of 0 and a maximum of 100, and we have a perfect visibility, meaning we have a perfect indistinguishability later on between the two photons of the pair. And if we have a visibility that is quite limited, we need to see if it's the setup that is limiting it, or if it's really something fundamental limiting the setup. So usually it's always something related to the setup, and sometimes we have ways to get rid of it and sometimes we don't. The values of visibility that are usually accepted in the literature are any visibility above 96-97%. Uncorrected, because sometimes people used to take raw data and do a post-processing. We need to have a non-post-process data that allows us to go to visibilities above 96-97%. Any other question? Yes.
Can you please explain more about decoherence and how to deal with it, or what it does to the lab?
Yes. Okay, so decoherence, as I said, it's good that this question was asked because it's one of the things I talk a lot about in class. So the problem of decoherence. Actually, as you know, in the classical world, so on the macro scale, we do not have any exhibition of quantum effects. You only see them at 3D, for example, at the scale of one photon, scale of a few atoms, etc. So the problem that we have is that decoherence is actually something, it's actually your system collapsing and losing either its superposition of state or its entanglement, and unwillingly. What happens is that sometimes you have those qubits, which can be electrons, photons, atoms. They start to do interaction with each other, and the system gets what we say between quotes measured. It means that it collapses. For example, if I have an entanglement of two photons of HH and VV, the system is either going to collapse to HH or VV prior to me measuring it. And when I'm using, for example, one qubit, which is in a superposition of state alpha 0 plus beta 1, when I'm working on the computational basis, I'm going to either get back to 0 or get back to 1 before I did all my measurement. Now, the problem of decoherence can be solved by working at very low temperatures, can be partially solved, shall I say, because the thermal energy contained within the qubits are something that create a lot of decoherence. But also the problem is that we need more qubits to do a faster quantum computing, but the more qubits we have, the more prone to decoherence we are. And the problem is that if we can do any quantum algorithm in a certain window of time that is less than the decoherence that is going to happen, then we're good. But if we need to work on certain quantum algorithms, such as the Shor factorization, where we are going to need a certain time, and our decoherence is too quick, then we're not going to be able to continue the calculation. We're going to obtain results which are very obsolete, which make no sense, and which is one of the problems we have in quantum computing, the verification protocol. How can we verify that a quantum computer is really doing its job? So for applications where we know the results, it's pretty easy, we just compare. But we have applications we are waiting for that we really want to do where we don't have any classical result. How can we make sure the quantum computer gave us the same result? That's where decoherence really is problematic. And are we ever going to get rid of decoherence? Who am I to say that? I don't know. We hope so. We are working towards that. So those are the unwanted, if you want, effects that are happening. Yes? Any other questions?
I actually have another question.
Yes.
For someone who's not enrolled in the Lebanese University, how would you suggest that he goes about pursuing a career or academic career in quantum information?
Okay, so at what level are you in? Right? Are you a grad student, PhD?
I am a senior DS student in GU.
Okay, so I would suggest to enroll our master's degree here in the Lebanese University because as far as I know, I don't think there are other universities in Lebanon that are giving full courses of quantum information. So for you to be completely prepared, like you have here the head of the master's department, you can talk with them on the coffee break. And I mean, once you do this course, I would say it's enough for one reason, for my personal experience, because when I did my master's degree, I did not have any course of quantum information. So when I went to my internship, because I started the internship prior to the thesis in the same subject, and that's where I learned everything. Of course, I had to see several courses, like when there was Damien and Eleni, they gave courses when I was doing my internship, and I saw their courses in order to start knowing what I'm actually doing, because I had no clue about quantum information whatsoever. So, I mean, once you have a good background in quantum physics, and if you want to do in quantum computing, a good background in mathematics, theory, algebra, then I think you'll have no problem pursuing a career in quantum information. Another question?
Please.
Yes. Okay.
Most of the advancements you're talking about the information are from an optics or experimental side. Is there another way to advance in quantum information other than what you have talked about today?
Of course. Of course. Now, what I have talked about contain a lot of theoretical things, because when we started the research with Rawad, we're not doing optics. We're not doing anything related to experimental optics. We're really working on theoretical aspect of quantum computing. So whether we're working with qubits, qubits, or systems that contain like n dimension, all of these are theoretical work. And actually, for me, it's now more interesting than the experimental part, because for the experimental part, I took a lot of knowledge from it. But the challenges are much different in the theoretical aspect, and you feel that if you reach a certain point in theoretical aspect, it's more satisfying. So the advances also that I have mentioned are just related to here what we did, not something worldwide. So now we are working on the theoretical aspect and everything related to doing modelization, doing analytical solutions. So. Yeah, the results that I got previous were, yes, that's only the part that we started like 4 years ago. That's not related to what we're doing now. What we're doing now is completely unrelated to my thesis subject, because I was into quantum communication, experimental quantum communication. I switched now to theoretical quantum computing. So I switched teams now. Okay.
One more question.
Okay, thank you. Sorry? Yes, for everything related to vibration, you mean? Yes, so for now we're not working with phonons, but there are quite a lot of work that is happening with phonons, especially when we work with condensed matter and quantum information altogether.
Because I read a few days ago not about phonons they are working on entanglement within the crystal. Instead of having this polarization stuff.
You mean they are more robust their entanglement is more robust, yeah.
You can see the phenomena of the entanglement within the phonon. Here you can see just getting it.
So you mean you can see, like you can measure it, or you can see how can? Well, I mean, it's not really something I'm working on, so I cannot give you an answer, but if it's true, well, yes. I've heard that there's a lot, some work including phonons for quantum information processing, but it's not something I really had some time to focus on. Any other questions? So thank you for your attention. Now I'm going to give the time to our sponsor to